Let's use another example. 3 5/10 times 1 3/10. For students to get a reasonable estimate of what the answer should be, if we were to round both of those down, we would have 3 times 1, and that would be 3. If we were to round both of them up, we'd have 4 times 2. So it's reasonable that our answer has to be between 3 and 8. So let's go ahead and multiply this out. So we get our first partial product, then we get our second partial product, and we get a 4, a 5, and a 5. And we've already estimated that our answer has to be between 3 and 8. So we know that the decimal point needs to go here. So it's going to be 4 55/100ths. Now, students are probably going to start seeing a pattern that, okay, I had one decimal to the right here, one decimal place to the right here, and I ended up with 2 decimal places to the right of my solution. So they'll get the idea of the standard algorithm or the standard shortcut, whatever you want to call it, that I had 2 places to the right in my 2 factors, so I should have 2 places to the right of the decimal point in my product. But that still doesn't really answer the question as to, well, why did this happen? So let's take another look at this, and let's use a concrete representation. 3 5/10 times 1 3/10. If we look at 3 5/10 as 3 1/2, well, this means that we're going to have 3 1/2 sets of 1 3/10. Okay, so here's one set of 1 3/10, and here's some more. So now we have 3 sets of 1 3/10 so far, but we need another. But that makes it 4 sets, and that's not what we want. We actually want half of this set here. Okay, and knowing that we are dealing with decimals, let's split this whole into 10 equal parts. There's 10 equal parts, so I only want half of them. Okay, so I get rid of 5 out of the 10. And now I have these 3/10 over here. Well, I get rid of 1, but that's not enough. That just balances out with this one here. So I've got to take this one here and get rid of half of that. So I split that up into 10 equal parts, get rid of half of them, and so now this is what we have. So to figure this out just using our concrete models, what we can now do is this. We can take that 1 and bring it over here and combine it with these over here. So now we have 10 of those tenths, which gives us another 1. And I think we have enough now to where we can figure out our solution. We have 4 1s. We have 5 tenths. And we have 5 100ths. So our answer is 4 55/100ths. Let's take the examples that we've used so far, and let's look at this from the big picture perspective. Let's go ahead and multiply these out like we were taught using the standard algorithm. We were taught to go ahead and multiply it all out. So we have all these whole numbers, and don't worry about the decimal point yet. Now, if we convert this back to fractions, okay, look what happens. On this first example here, 4 times 2 is 8. On the second example, 3,723 times 5 gives us the 18615 there. And then over here, 35 times 13 gives us the 455. So there's a direct correlation here that, okay, I just multiply here and don't worry about the decimal points. Well, the same thing happens here with the fractions, okay? Multiply the numerators. Now look at the denominators. On this first one, we have 10 times 10, which is 100. So we have 8 hundredths. And so now we know that our decimal point needs to be over here. We'd have a 0.08. Over here, we're going to have 18,615 divided by 100. So we'd have to move our decimal place. The same thing over here. We're going to have 100 in our denominator. So there's a definite pattern here. If we look at this in terms of the fractional representation and connect it back to what happens with our rule as far as what to do with the decimal point, it makes sense. So again, this is what would happen in each one. It just so happens that the denominator for each one of these is 100, but it still connects back to where if I'm dividing by 100, it's the same thing as taking my decimal point and moving it 2 places to the left in each case. So again, a very definite connection here, and it adds a lot of understanding as to, well, why is it that you move the decimal point as many places as you do? So, for example, if this over here would have been something to where we would have ended up with 1,000 in the denominator, then we'd be dividing by 1,000, which means we'd have to move our decimal place 3 places to the left. Or if it was 10 in the denominator, we know we'd have to move 1 decimal place to the left. Again, the connection to the fractions enables us to make sense of what happens as far as why you move the decimal point the number of places that you do. Now let's look at division, and that's going to be probably the more difficult of the 4 operations. Let's use 2/10 divided by 4. Connecting this back to the standards at this grade level, remember that dividing by fractions, we were limited to dividing a fraction by a whole number or a whole number by a fraction, and that's exactly what the correlation that we have here with decimals. So we're going to have a decimal here, 2/10 divided by a whole number 4. We're going to focus on properties of operations also. Now, what happens here is that it's very important that students are flexible in terms of how they interpret the symbolism. One of our properties is that division is the same thing as multiplying by the reciprocal. What we have here then is we're going to take 2/10 and we just want 1/4 of that. Or another way of thinking of it is we have to take 2/10 and split it up into 4 equal parts, and again we only want 1 of those. So we take our unit whole, split it up into 10 equal parts, and get rid of 8 of them, so we have 2/10. So now we need to split that up into 4 equal parts. We only want 1 of those. Now the problem is, what size are these? What do they represent? Okay, I've got 2 of them, but 2 what? Well, let's go back. We had 10s this way, and then if we continue these horizontal lines out, now we can count them out and see how many of these we have. And if we count them out, it's 10 by 4, so we have 40 of them. So actually what we have now is 2 over 40. We have 2/40ths. Each one of these little shaded areas is 1/40th of the area of this unit square. But our problem is we have to express this as a decimal, and we have to deal with subdivisions of tenths, hundredths, and so forth. So what we need to do here is subdivide this into 100 parts. But it's hard to tell here, and the problem that these red lines represent division into 4 equal parts, which doesn't exactly coincide with dividing it into the 100 equal parts. So let's blow this up a little bit so we can see a little bit better. So here's what we have. Each one of these is 1/100th, so we have 4 of those. But notice here, these got cut in half. So each one of these is half of 100. So you can combine these two, though. If I move one of these over here, then I have another 100th. So now we know that we have a total of 5 100ths, which as a decimal would be 0.05. And that is equivalent to our fraction of 2/40ths. Now let's look at this a little bit more algebraically and not be dependent on the physical model. So we ended up with 2/40ths. Now if we were to divide that by 1, nothing would change, but now we need to be a little creative and change the 1 to dividing by 2 and dividing by 2. So 20 divided by 2 is 1, 40 divided by 2 is 1/20th. So we simplify the 2 over 40, but we got 1 over 20, which still doesn't help us as far as what to do in terms of a decimal. Well, now if we multiply by 1, well, let's see, what do we need to multiply the 20 by to get 100? Oh, a 5. So let's just make this multiplying by 5 over 5. And so we get 5 100ths. And that corresponds to our previous work. So we know that as a decimal it would be 0.05. Let's take another approach. Let's take our 2/10 divided by 4 and change it to multiplying by the reciprocal, which would be 1/4. We're using our properties of operations here. But let's go ahead now and just deal with fractions. So we'd have 2/10 times 1/4, which is 2/40, which puts us back where we were earlier, and we would finish it off using the same process. Okay, another look. We have 2/40, and if we look at this in terms of our division algorithm, we would be taking 2 and we're dividing it by 40, and we already know the rules as far as our standard algorithm for division. 40 will not go into 2. Don't forget your decimal point, it comes straight up. 40 still doesn't go into 20, and then we go another decimal place, but 40 does go into 200 5 times, and we get the solution that we got previously, 5/100, 0.05. What we can also do is take our original representation as a fraction. We'll have 2/10 over 4, and if we do this in terms of the standard algorithm, bring our decimal point up. 4 does not go into 2. 4 does go into 20, however, 5 times. And so again, we end up with the 5/100 yet again. Let's switch things around this time. Now we're going to have a whole number divided by a decimal. Okay, 4 divided by 2/10. How should we interpret this? And let's use a concrete model. Well, we have 4 wholes, and we're dealing with tenths. So basically what this is asking is how many sets of 2/10 are there in 4? And so we split each one of these up into 10 equal parts, but we don't want just 1/10, we want 2/10. So if we split this up into sets of 2/10, here's what we have, and we make them different colors to differentiate them. Then we do the exact same thing with the rest of our wholes, and so if we count them up, we have a total of 20 sets of 2/10 each. Now if we try to do this using our standard algorithm for division, okay, well, let me see. 2 into 4 goes twice. Okay. A little confused. We know the answer is 20, but if we didn't know that already, where's the decimal going to go? It doesn't come straight up. It's over here, so it's confusing. So this is a little bit of a problem. It's really hard to determine what to do with the decimal place when you're dividing by something that is a decimal. If your divisor contains a decimal, then this totally changes the picture. So now what? What would be a good way to alleviate this? Well, as a fraction, this would be 4 over 2/10. But we already saw that that was a problem. Well, we know we can multiply by 1, and what's messing this up is having 2/10 in the denominators. Well, we can multiply by 10, and that would fix that problem. So this then converts to 40 over 2. And this sure makes it a lot easier in terms of the division by the standard algorithm. So if we add a 0, move our decimal place 1, which was indicative of multiplying by 10. We have to move the decimal place here too, which was what happened over here when we multiplied 2/10 times 10. So now there is no confusion. I knew exactly what to do with the decimal point. My decimal point is here. I did the division. The decimal point just comes straight up. But as far as the model, 40 over 2 is a little bit different than what we had earlier, because now we have 40, so we'll represent those with 40 of these little rods. Okay, so we got 40 of those, but we want to know how many sets of 2 there are. So there they are, and count them up, we get 20. But it's a little bit different because now again we had, the question was how many 2s are there in 40? Take another example. We have 13 and 4/10 divided by 8/100. What makes this difficult is all of these decimals, so let's do something about it. What we can do is multiply the numerator and the denominator by 100. That's multiplying by 1, so it doesn't change the value. So if we do that, we do ourselves a favor and we got rid of all of our decimals. So if we do that, an equivalent problem to 13 and 4/10 divided by 8/100 would be 1,340 divided by 8. And this is a lot simpler in terms of figuring out our solution, where the decimal point goes, and so forth. So what we've done then is we multiplied both of these by 100, and that adds understanding to, well, why is it that I moved at my decimal place 2 places? Okay, well, now again it's a little bit more obvious because again, if you connect it to what happened over here, we multiply both by 100, which again connects it back as to why we're moving the decimal place 2 places here and 2 places here, because we converted this to an equivalent problem, 1,340 divided by 8. And so now, again, the solution is a lot simpler. We know exactly what to do with our decimal place. We do our division, and voila, there's our solution. It's 167 and 5/10. The last part of the standard, we've been pretty much doing this all along. We've been relating the strategy to a written method and explaining the reasoning used. As far as the standards for mathematical practice, if we look at the first 4 and then connect that back to the activities that we have done here, we have done 2, 3, and 4. We've reasoned abstractly and quantitatively. We've constructed viable arguments and critiqued the reasoning of others. We've modeled with the mathematics. And then if we look at the last 4 standards for mathematical practice, based on the activities that we did, we used appropriate tools strategically. We did attend to precision, and we did look for and express regularity in repeated reasoning. That really helped us, number 8, to make sense of why we do what we do with the decimal points with the 4 operations.